Hello everyone, welcome to my video series on statistical significance testing. So today we are going to talk about Spearman correlation coefficients and the p-value. So let's dive in. So first of all, let's look at this plot. So we are trying to measure the correlation between the variable x and variable y, and we can see some points here. They are clearly very much correlated, and their correlation coefficient is basically 1. I'm going to show you how to calculate these in a second, but let me first give you some examples. This is another one here. The x and y aren't really that correlated. You can see that the points are scattered all over the place. So here the correlation coefficient is only 0.3, so weak correlation. Here you can see that the correlation is actually negative. So when x increases, y actually decreases, right? So you can see y is decreasing. So it's a negative correlation. So both the first case and the third case are strongly correlated, but it's just that one is positively correlated and the other one is negatively correlated. Now, the first question we are going to try and answer is how to calculate correlation between x and y using Spearman correlation. And number two is how to see whether the correlation is statistically significant or not. So whether the p-value is low or not. So let's try to answer these questions now. So this is the data of this particular plot, which had a correlation coefficient of 0.3. So this is how the x and y actually look like. So we can put some ranking right here like this. So you can see that 10, 20, 30, 40, 50, these are ranked from 1 to 5 because they are clearly like increasing gradually. And here you can see in the y that 1 is here. This is the lowest ranked. 2 is here. This is second lowest. Then comes 30. This is 3. Then comes 40. This is 4. And then comes 50. This is 5. So these are the ranks. So what we are going to do now is we are going to make this nice little table right here. You can see rank x 1 to 5 and rank y 3, 2, 4, 1, 5, 3, 2, 4, 1, 5 right here. So first of all, what we do is we get the difference between them. So 1 minus 3 equal to minus 2, 2 minus 3 equal to 0, 3 minus 4 equal to minus 1, so on and so forth. And finally, we get the d squared. So we get these values right here. So it's not very easy to sum these things up. Summation of d squared equal to 14. And so this is basically your correlation formula, right? Now this formula looks a bit hideous. I will explain in a second how this formula actually comes into being. So 6 is just a constant and 1 is right here. So this is di squared. So this is going to be 14. And n is basically number of samples. So you can see that there are 5 samples here, 5xy pairs. So n is going to be 5. So you can plug in these values here and you can see that we are going to get 0.3, which is a weak positive correlation. So I think so good so far. But one thing we wanted to answer is this. So where did the correlation formula come from? Right, that hideous formula that we just saw. So first of all, this is the correlation formula. So this is basically very fundamental. If you do know about correlation, you know about this. So correlation between x and y is the covariance between x and y vectors. So x is a vector because x had 5 values right here, and y is also a vector, y also had 5 values. Sigma x is standard deviation of x and sigma y is standard deviation of y. If you plug in these values, you can get the correlation R. Now, for Spearman correlation, we are more worried about the ranks. So we deal with ranks because it is a non-parametric test, as you already know. So we replace x by Rx, that means rankings of x, and we replace y by rank y, rankings of y. So the formula will look something like this right now. And I have replaced rho with R because this is what we use for Spearman correlation notation. Now, here is the interesting part. So each rank variable Rx and Ry, they will go sequentially, right? Because they will be from 1 to n. So you are not going to have like 1, then 5, then 20. You are not going to have values like that. You are always going to have values like 1, 2, 3 up to n, right? Okay, if you have this assumption in place, then you can actually do some algebra right here, which I'm not going to show in this particular video. That's out of the scope of this video. You are going to actually transform these formula into this formula right here. Okay, so that is intuitively how the formula actually comes into play. Okay, now let's try to answer the question of how the p-value is obtained. So the null hypothesis H0 is this, very simple. There is no correlation between the two variables x and y. Absolutely simple. So what is the H1 alternative hypothesis? This is that there is significant positive or negative correlation between x and y, right? So it can be positive or negative, doesn't matter, but whether it is positive or negative, there will be an extreme p-value. That means a very low p-value basically. Okay, let's see how to get these things. So first of all, let's try to understand the H0 a little bit better, right? So suppose we randomly pick n values for x and n values for y. We randomly do this. It is not given to us. Suppose we randomly like pick 5 values for x for this example and 5 values for y for this example that I'm showing you. And we get the row value for that. That means we get the Spearman correlation for that using the formula that I just showed in the previous slide. Okay, so we have one row value right now. Now we can actually do this many times. We can basically pick n values for x and n values for y and get the row value many times, 5, 6, 7, 8, 9, 10 times maybe. So if we do this 10 times, we are gonna get 10 row values, right? Many means 10 row values if we do this 10 times. Now, these row values right here, they have resulted from random picking of x and y. Now, if you have followed my series on probability distribution before, I have it in my channel already. So you can see that these random pickings or random sampling will actually result in normal distribution. Now, normal distribution turns into t-distribution when you have small number of values. And so this whole H0 can be approximated by a t-distribution. Now, again, if you don't understand this line right here, I will actually recommend you to check my video on normal distribution and t-distribution because that's where I explained normal distribution and how it turns into t-distribution in more detail. But if you know those things already, then obviously you understand what I'm talking about. So this is the formula for t-test for the t value, the t variable. So rho is the variable that we are actually like using to form the distribution itself. So this is the variable. So rho into root n by n minus 2 divided by root 1 minus rho square. So n minus 2 is nothing but degrees of freedom because we know that if we want to do some regression, we need two things, the slope and the intercept. That is why we need at least 2 points. That is why the minus 2 is right here in place. And understand that in this formula, if we have a large rho value, then t value will be larger, right? So suppose rho value is 0.9, then this t value will also be much larger compared to when rho value is 0.1, right? So this is something you need to understand in detail. So basically what I'm talking about is this. So if you have a large rho value, you are going to have a large t value. And if you have a small rho value, you are going to have a small t value. Here is the very interesting part. If you have a large t value, then that t value will correspond to a small p value. Why? Let me intuitively explain to you. So normally in a t distribution, the t value is going to be large only when you are basically at the limit, at the two tails of the distribution, at the limit. That means you are in extreme case, then there will be a large t value. And that is why the p value will be small. That means you are going to be able to reject the null hypothesis. Okay. So for example, suppose rho equal to 0.3, which is a small Spearman correlation, and we have a small sample size of 5. You can do the math here, and you can get a t value of around 0.54. And for that, you can use this t table right here. So there are t tables available all over the place. You can just search it up from Google, or you can even ask ChatGPT. So for example, for df equal to 3, here df equal to 3, right? Because n equal to 5. And df, that means degrees of freedom, equal to 5 minus 2 equal to 3. So for different degrees of freedom, this table is given for different t values. So let me explain this in a bit more detail. So for example, for df equal to 3, we have all these t values and all these p values right here. Again, for df equal to 4, we have another such table. For df equal to 5, we have another such table, and so on and so forth. So here, since we have 5 samples, we are using the table for df equal to 3. And you can see that for around 0.5 value of t value, we are going to have a p value of around 0.65, right? That is what we are actually getting here. And so for this case, we cannot really reject null hypothesis. That means the correlation is not significant, basically. So the null hypothesis cannot be rejected. So if we have a much higher correlation with the same number of samples, we're going to see a much higher t value. And for the much higher t value, we're going to have this very small p value. So this is statistically significant. So you can reject the null hypothesis, and so correlation is significant. Finally, you can also have the negative correlation, which was the case 3, which I showed you in the first slide. And in this case, we're going to have a negative t value. And obviously, even for negative cases, p value will be very small because this is a two-sided test, right? This is a two-sided test because we don't care about whether the correlation is positive or negative. We just care about whether the correlation is significant or not. That's why. Okay, fine. Now that you understand this part, last part I want to discuss is when to use this correlation. This is very, very important question. So the first thing I want to mention is when you measure correlation between two variables that have different metrics of measurement, then you definitely need to use Spearman correlation because then you need to sort of know whether the increase of one variable also causes an increase of another variable. right? So you just measure increase or decrease. You don't care about the actual value itself because the metrics themselves are different, so rank comes into play. For example, if you want to get the correlation between temperature and humidity, so temperature has a different metric of measurement, humidity has a different metric of measurement, so they are both different. Also, if you want to measure the correlation between mutation frequency and tumor fraction, two very different things, but can be found in the same human body, and you can try to do that as well. One thing I didn't mention here is you can use Spearman correlation for any pair of variable correlation analysis. They don't need to have any specific distribution because there is another type of correlation measurement, which is this Pearson correlation, which I will talk about later on in this video series. But Pearson correlation can only be used for certain types of distribution, but Spearman, it doesn't have any such limit. You can use it with any metrics you want, any distribution you want. That's the beauty of this distribution. That's the beauty of Spearman correlation, basically. So that's all about this video. So if you feel this video was helpful, feel free to subscribe and share. And there's a donation link in the description. You can donate to our channel to support our cause. Thank you very much.